Hi, welcome back. In this lecture, I would like to talk about hybrid programming with the MPI shared windows. So this is an alternative to use MPI plus OpenMP or MPI plus P threads, and basically corresponds to use MPI plus MPI. Let's look at this. So very recently, MPI 3 allows different processes to allocate shared memory through the MPI interface. So we can use the MPI win allocate share to allocate share memory. So the way to do that is basically to make a windows and declare that it has been shared between the processes. So these share windows will basically map to the shared memory of the computing node. So since this is a window, we can use many of the concepts that we have been seeing in the one-sided communication. So we can make the windows and then write or read using put and get operation. Application can do hybrid programming using MPI or load and store accesses on the shared memory windows. Other MPI function can be used to synchronize access to shared memory regions. Remember, so basically we're using MPI one-sided for doing operation on a shared window. So in some sense, can be simpler to program than actually to couple with the OpenMP threads. So how this is going to work? So in this case, we have 3 nodes in pink, and then we have 4 processes per node. So we start our MPI application with the MPI com world that will consist of basically 12 MPI processes. The first step we need to do is basically to split the communicator in 3 shared memory communicator. So for doing that, we use the function MPI com split type. So we go from our MPI com world communicator to shared memory communicator. And then you're basically using this split type shared communicator to allocate the windows that have been shared within the nodes. And for doing that, we use MPI win allocate shared. And this will create our shared memory window. So shared memory windows allow application processes to directly perform load and store accesses on all the windows of the memory. So on the local memory, we can do just load and store, like in this case, we basically write a 10 to this element of the X array. But also we can write to the local memory of another process by just using put. If you want to read, then we can also do a get and send from the other process memory to the local process, just using MPI windows. So all the existing RMA function can also be used on such memory for more advanced semantics such as atomics operation. So for instance, we look at MPI, accumulate, and so on and so forth. Can be very useful when processes want to use threads only to get access to all the memory on the node. So for instance, you can create a shared memory window and put your shared data. How the memory allocation and placement works? Well, shared memory allocation does not need to be uniform across the processes. This means that processes can allocate a different amount of memory. It can be also even 0. The MPI standard does not specify where the memory would be placed. For instance, which physical memory will be pinned to. Implementation can choose their own strategies, though it's expected that an implementation will be try to do the optimal things, that we will try to place shared memory allocated by a process close to it. The total allocated shared memory on a communicator is continuous by default. User can pass an info hint called a non-config that will allow the MPI implementation to align memory allocation from each process to appropriate boundaries to assist with the placement. So this is an example of shared of using the share windows with the MPI. So we start with our array. We get our com world. We then split MPI com world using MPI com split type, and we take and we get communicator that are MPI com type share. Once we have our communicator here, that is the type of MPI com type shared, we can actually allocate our window using our allocator and getting our window. We then can start our operation on the shared memory by basically starting the epoch, MPI win local, and then and stopping it with MPI win alloc all. So all the one-sided operation will occur here. So in summary, we have been looking at how to couple MPI plus X. So MPI plus X is a very reasonable way to handle extreme parallelism. So if you want to go to very large and system and use very efficiently, we need to couple a model for distributed memory programming, that is MPI, with one model that is doing the nodes, the multi-threading on the nodes. So extreme parallelism calls for MPI plus X model, but also if we are basically just programming shared memory nodes, other hierarchical memory architecture might need this MPI plus X. So there are many choices for X, can be OpenMP, can be pthreads, but also can be MPI itself using the MPI shared memory. This is the last slides, and talk to you soon.